So so today I'll just go through really briefly about why spatial temporal data is exciting, but of course there's a lot of challenges working with spatial temporal data here. So I guess some of you have worked with all kind of spatial temporal data, whether it's actually data coming from the web, from social media, which could also be considered spatial temporal. If it has spatial reference, can come from even web data and time series, typically as well with spatial reference. Now, the problem is, although we think they are big data, but they're not as pretty as we think, because before we get into modeling, and I don't have to preach to the crowd, that just treating everything as, we can actually just do a typical regression or classification task is not that easy if the data is not reliable, or it's not enough volume data, and even the observation is not enough for us to build a reliable model, and perhaps the data is not properly labeled. So there's a challenge, of course. The goal is to achieve high performance AI system, but how do we do so with limited observations? And this is especially very important if we actually working with real world data. Now, there are a couple of strategies that have been explored in the machine learning community, which includes, we extrapolate from data, either from small data sets or collections that are properly labeled. For example, if for classification tasks, we can use something like, for example, weakly supervised learning, or we can also use adversarial learning then to generate synthetic data, which was also covered previously in the previous talk. I'll talk about that a bit more in this talk as well. And we can also then look at a way of extrapolating to a new domain or task, either we transferring an established knowledge to a new domain, or we can actually learn from auxiliary tasks or perform even a pre-training task that's actually generalizable. Now, I'll just talk about the second part really briefly. So today, I'll just really briefly talk about 3 different things because we don't have much time: GAN, transfer learning, pre-training. But I'd like to actually cover more on this topic, GAN for spatial temporal data, because this is a survey that was recently accepted at the ISD. So I hope this could be a great resource for everyone in this call. So there are a lot of for what makes a certain data called ST data. So it has spatial reference, temporal reference, that's very easy. Autocorrelation, so basically data that are closer together in space or time, they tend to correlate. And it also depends on the regularity. It can also inform the regularity and all those behaviors and the trend. And also another property that's actually a lot of people realize, and that spatial temporal data is not that easy to deal with because it's heterogeneous. Actually, if you want to create a synthetic data that is reasonable, we need to actually account for the heterogeneity, and the heterogeneity here also includes the dynamic patterns in the spatial temporal data. So there are different types of spatial temporal data. You can look at a paper of different definitions, from event data, trajectory data, raster data, graph data, or time series with spatial reference. But even sometimes spatial reference is missing, so it could be sporadic spatial references. A lot of examples there covering the papers, a lot of different data sets that have been used for in a lot of different GAN papers. So I'm just going to skip that. So this is the basic architecture of GAN. A lot of people here may know it, so I won't actually go through, but the main thing is you've got the generative component, discriminated component, and with the random noise generated by the generator, used by the generator, then discriminator will actually then use the loss function to distinguish whether the data itself is real or fake. So the very basic of it is actually a vanilla GAN. So you can see here, this is an example of vanilla GAN. We have discussed different architecture of GAN in our survey paper as well. From vanilla GAN to the more recent info GAN or semi-supervised GAN. The different versions here is where do you put the labels in the whole architecture? Where do you actually start using that, and when do you actually start synthesizing information between the fake and real, and where do you actually backpropagate? So For GAN on spatial temporal modeling, there are a lot of different tasks that has been addressed in the literature, from for prediction tasks, data generation tasks, data imputation tasks, and also graph representation tasks. So as I said before about, for example, heterogeneity of spatial temporal data, if they're actually represented as certain type of graph, they may not be homogeneous graph, they could be heterogeneous graph, and how would you actually fuse them together, and GAN could be used in that purpose as well. This is just a quick example, GAN for time series imputation that was quoted, also cited in our paper. And here, this is a range of data sets that we actually found that have been used in the past by literatures, and they actually generated a lot of, either they use it for different purposes, not only synthetic data generation, but it could also be used for prediction. Now, I've got a list of open challenges as well. Again, see the paper. A lot of GAN work are designed for image generation, and we know that for this is actually very different for spatial temporal. So what works for images may not work for spatial temporal and time series data, and therefore the loss function, for example, you know, KL divergence, Jensen-Shannon divergence, and all that may not always directly be applicable for the problem that we are interested in. So they have some kind of more customized loss functions for ST-GAN. Evaluation matrix is really difficult because you can use an external evaluator for, you know, images, for example, but for spatial temporal, it's harder. You can, of course, use something like, you can treat it as a prediction task. You can use the standard MAE or MSAE kind of evaluation matrix, but, you know, then you can actually use it as, at the end, a downstream, not really within the architecture itself, within the pipeline. So designing the right evaluation matrix is hard. And one more thing about, I saw one of the comments in the notebook that people are interested in privacy preservation. I just need to say as well, adversarial learning does not guarantee privacy preservation. We discussed this in our recent paper called Deep Obfuscator, because you can still always get an adversarial attacker to actually discover the private attributes. So we actually have a paper currently under review where we actually use spatial temporal GAN network that is also guaranteeing privacy preservation in combination with differential privacy. So we have another follow-up work. So a very quick, I don't know, I think 2 minutes, 3 minutes. A really quick, sorry, 3 minutes. A really quick example where we use GAN, for example, in here, when we need to perform terminal comfort prediction in multiple cities. Terminal comfort is basically done normally as a survey with -3 and +3. This is very important for a lot of building scientists and architects, so they can design better buildings based on the different design of the building. And as you know, survey data is expensive, and we actually our clients need us to build some kind of I mean, our industrial partner to us build some kind of a thermal prediction. Thermal comfort prediction model, but if there is no survey data, how would you do it? So we actually, for example, we use source data set that's collected by ASHRAE, and this is collected from 52 cities over 13 climate zones, and also the Skills project. Now, the thing is, some of these data completely imbalanced. Survey data is completely imbalanced. So we use tabular GAN, for example, to actually help with the class imbalance. And then we use this as a target data set, office building Philadelphia for over a year to predict the thermal comfort. I'll just skip that. So basically, the result is using transfer learning in addition to the help of the synthetic data generated, the survey data that's generated actually boosts the prediction performance without using the transfer learning in that. So another quick example I'd like to show you is this is the work published at PERCOM where, you know, we have a smarter city and suburb grant project with Mornington Shire. We have sensors installed, parking sensors installed in Rye Township, and that was installed in January, and it's only operational from February, mid-February. And you know, March we had lockdown. So they want one of the deliverables of the project is to deliver a reliable parking availability prediction. But as you know, we can't do reliable prediction with that long history. So, but we have access to Melbourne CBD data. So what we did was we actually use a domain adaptation from Melbourne CBD to Tri Township. So this is we use adversarial domain adaptation in a few short manner. So this is a comparison of the 36 million records from Melbourne, whereas in only a couple hundred thousand records from Rye. I'll just skip that. But what is important to see here, we adapted GAN. We don't use the whole GAN architecture. We just basically use the domain discriminator to actually discriminate the latent features that are similar between source and the target domain. And then we use, then only we look at we use a classifier in a downstream task to then see whether domain discriminator can be used to predict a certain trend. So this is a regression problem. So so we actually use it using the domain adaptation and the discriminator. It actually really helps. Even just with 6 days of parking data, we can achieve a really good prediction accuracy with the help of Melbourne City data. And really final one is without, if you really have no label data at all. So for example, in this problem, we in a paper we had published recently in KDD for COVID-19 classification, you can also use the concept called contrastive pretraining. And in here, with a combination of random masking, we could actually achieve good performance, even beating the classical supervised learning model.